Today we will be continuing with chapter 14, experimental techniques and chemical analysis, and we are talking about how to separate mixtures. We've covered separating solid liquid mixtures all the way up till simple distillation. And so today we are going to start off with separating liquid and liquid mixtures. So in recent years, there have been several oil tanker accidents that have led to environmental disasters, just like the one shown in the picture below. These have resulted in millions of liters of oil being washed into the sea. Oil and water do not mix easily. They're said to be immiscible, right? So immiscible is the term used when you've got two liquids, and despite being liquids, they do not mix together, right? Because being a liquid is a physical state, which depends on how closely packed the atoms or molecules are, and uh, how much energy those particles have. Whereas the mixing depends on the properties, uh, right? Whether they are ionic or have charges or not, right? And stuff like that. So when cleaning up disasters of this type, a range of chemicals can be added to the oil to make it more soluble. This results in the oil and water mixing with each other. They are now said to be miscible. So if they can mix together, they're miscible. Right? So water and, let's say, vinegar, right? They mix together, so they're miscible. The following techniques can be used to separate mixtures of liquids. So first of all, if we have a mixture that itself is immiscible, so those can be separated using a separating funnel, like you see over here. You've got these two liquids, whatever they are. They might be like water and oil or honey, for example, or water and oil. And so the mixture is poured into the funnel. It is allowed to stand so that it separates into layers, as you can see. And then the lower layer can be run off by opening the tap. There's a tap over here, and so you open the tap, right? You've put you've attached the separating funnel to the clamp of a retort stand. Open the tap of the funnel, and you let the liquid run into a beaker, right? Whatever size it is you need. This one's 400 ml or 400 centimeter cube, the beaker. And you run it as close as possible as you can to the end of the blue liquid and where the red one's starting, being careful that you don't mix the red one. And then you change beakers and you pour the rest of it. Right now, this isn't like a perfect separation. There is possible that some of it will be left over, right? Some of the blue liquid will be left over with the brown or red liquid, whatever color you want to call that. So it's not perfect, but it does help. And right, density also plays a part over here. So the blue liquid is below the red liquid because it is denser, right? So density does play a part. It's not necessarily the only factor which makes it immiscible, because honey is denser as compared to water, but they are miscible if you stir them, right? So honey will mix in water. On its own, they're immiscible, so they won't readily mix together. But oil and water are immiscible. Even if you stir it, as much as you stir, it doesn't matter, right? They won't mix. And oil is less dense than water. So things to keep in mind. Then you got miscible liquids. So if they are to be separated, then this can be done by fractional distillation. Right, so it's distillation, but more advanced, right? And we've come across fractional distillation when we were talking about separating the fractions of crude oil, right? Back in the chapter of chemical energetics, I believe. So the apparatus used for this process, you can do that in the laboratory as well. It's shown in figure 14.18 on the next page, and could be used to separate a mixture of ethanol and water, right? So ethanol and water, that's alcohol and water, can also mix together. This is the setup, just to show that quickly. So you've got the mixture over here, you're heating it, right? It depends, right? So this depends on the boiling point of the two liquids, and they should be considerably different. So one liquid boils first, it moves into the fractionating column, right? And there's short lengths of glass rods inside, increased surface area, moves through that, goes up, and then right again through the Liebig condenser, which has a cooling jacket around it with water passing through it. It condenses. The distillate is collected, sorry, into a flask, and then once at that boiling point, all the liquid is turned to gas and then collected, and you raise the temperature further, and you see that no other, like you're not getting any further gas. That means all of that liquid has been collected, and then you can either continue that process for the other liquid up to the boiling point and collect it separately, right? So you can do that. So going to the explanation in the text. Fractional distillation relies upon the liquids having different boiling points. When ethanol and water mixture is heated, the vapors of ethanol and water boil off at different temperatures and can be condensed and collected separately. Ethanol boils at 78 degrees centigrade, whereas water at 100 degrees centigrade. When the mixture is heated, the vapors produced is mainly ethanol with some steam. Okay, that's where the glass rods with the surface area come in. Because water has the higher boiling point of the two, it condenses out of the mixture with ethanol. This is what takes place in the fractionating column. So these glass rods, right, what they do is they increase the surface area. So as the ethanol is rising as vapors, it's hot enough to rise all the way up. You've got a thermometer for the temperature. And we know that if there's heat, right, you'll have some evaporation of water as well, because evaporation can happen at temperatures lower than the boiling point of the liquid. And so, right, the steam or the water vapors will, hit the surface of these glass rods and condense and move back. And so what you'll be able to collect is purely ethanol without any steam and any water mixture. The water condenses and drifts back into the flask while the ethanol vapors move up the column and into the condenser, where it condenses into liquid ethanol and is collected in the receiving flask as the distillate. When all the ethanol has distilled over, the temperature reading on the thermometer rises steadily to 100 degrees centigrade, showing that the steam is now entering the condenser. At this point, the receiver can be changed and the condensing water can be collected, and you separated your two fractions. Okay. Fractional distillation is used to separate miscible liquids such as those in petroleum, which we've covered in chapter 6. And the technique can also be used to separate individual gases such as nitrogen from the mixture of from air, right? So air is a mixture of gases, as we know. And so,
Miscible liquids are the one like that can be mixed easily.
I'm sorry, could you repeat that?
Miscible liquids are the ones that can be mixed easily. No?
I'm still unclear as to what you're saying. Your voice is a bit mumbled. If you could just speak a bit louder, like.
Yeah. Miscible liquids are the ones that can be mixed easily. No?
The liquids, the thing is, like, they need to be like, the difference in the boiling point should be uh, you know enough to be able to separate them through heating, right? So if, for example, ethanol is at 78 degrees centigrade and you have another liquid that's maybe at 82 degrees centigrade, and so the boiling point is close enough that maybe you won't be able to do fractional distillation effectively, maybe, right? Because it's very close. Uh, you can separate the liquids easily if that's what you were saying. So yeah, I mean, it takes time, it takes a setup, but it can be done. Again, it depends on the difference in boiling points. That is crucial.
Okay.
Okay, so right, there's fractional distillation of air to separate the different gases, and I believe what they do is they liquefy. Have they mentioned the details over here of how fractional distillation of air works? No. Right, so they liquefy the air and then they do fractional distillation. There's right, separating solids and solids. So I mean, in this case, they're using electromagnets. It's going further, so it's not part of it. You don't need to know this part for your examination purposes at least. So, right, in this junk pile, what they're doing is they're using a strong electromagnet to at least separate metals from non-metals, right? And right, separating solids from other, like one solid from the other, also depends on their properties, right? So being metallic or non-metallic, or in this case, what they're showing is if they're heating a mixture that something that's mixed with iodine, and so they're heating it, so iodine will sublimation is when a solid turns directly into gas, so it doesn't go through the liquid phase, right? So when you heat solid iodine, it's sublime, so it makes iodine vapors, and so those iodine vapors can be condensed on an inverted filter funnel and removed or collected elsewhere. So there are other techniques as well, right? And solvent extraction. So if there are two solids that have different properties as to what they can dissolve in, right? So one is soluble in water, the other is not soluble in water. For example, you have a mixture of, let's say, salt and sand, and you want to separate that. So you know that salt can dissolve in water, sand cannot. And so you put that mixture into water, you stir it enough that you're confident that all the salt has dissolved in water. Then you let it stand, so the sand will not dissolve, it will settle. You remove the water, or you filter it out. you so you've removed the sand, and then by evaporation you can collect the salt back and remove the water. So it's a long process, but it's possible, right? So that's, for example, solvent extraction, using organic solvents to separate sugars, right, and stuff. Again, it's going further, but just so you. Right. So another method for separating two liquids is chromatography. So sometimes we need to separate two or more solids that are soluble, right? So in this case, it's not exactly a liquid, it's soluble solvents. For example, mixtures of soluble colored substances such as inks and dyes. A technique called chromatography is widely used to separate these materials so that they can be identified. Right, so it's not actually like sort of separating the different materials in the mixture, but you take a sample of the mixture, and in that sample you separate them so you can identify, oh, so the mixture is made up of this and this, right? And then you can perhaps use some other technique to actually separate the contents of the mixture, the components of the mixture, or maybe the purpose was just to identify what the mixture is made of. There are several types of chromatography, however, they all follow the same principles. The simplest kind is paper chromatography. To separate the different colored dyes in a sample of black ink, a pencil line is drawn about 1 centimeter from the bottom of a piece of chromatography paper. So it's like a special kind of paper. It's not like you take your regular notebook paper for this. This is called the baseline, right? So we can take a look at this, right? So this is the chromatography paper piece over here, and this is a line that we drew. This is called the baseline, and you put a drop or a spot of the sample on the baseline. Right. Do not use a pen to draw the baseline, as the dyes in the pen ink can also get dissolved and can also it can mess up your results basically, right? Interfere with the results because you're going to use a solvent, and so the ink from the pen can also dissolve in the solvent, and it will also take part in the chromatography, and so you get incorrect results. A spot of the ink. Assalamu alaikum, Sabi.
Walaikum assalam.
Doing well?
Yes.
Okay. So a spot of the ink is put onto the pencil line on the chromatography paper. This paper is then put into a suitable container, such as a beaker containing a suitable solvent. This is suitable solvent because you can have different solvents, and the result that you get will depend on the solvent that you've used. So, right, they'll talk about that obviously. So ensuring that the solvent level does not reach the pencil line. So you want to keep the solvent level below the pencil line. And the reason why you want to do that is, if you keep it at the pencil line where you've put the drop, the sample, then that will start dissolving in the solvent in the beaker, and that's the end of your investigation right there. So you want the solvent to be absorbed up the paper, and as it is absorbed up the paper, it will dissolve the ink, and then the different dyes or pigments in the ink will move with the solvent to different lengths. So, right, you need to ensure that the solvent level does not reach the pencil line. A lid is placed over the container to reduce evaporation of the solvent. Okay. So, right, baseline spot, you put it in a container, you cover it, there's the solvent, and the solvent is not reaching the pencil line. You leave it so that the solvent is soaked up the paper, and as that happens, right, the distance that the solvent travels is called the solvent front. Right, so you'll see it like a line, because obviously it's soaked, so it's going to be wet. So you can see that, and as it travels, you saw that it was black, but as it travels, you see that the different dyes in that ink, black ink, are separating, and when you're done, at the end, you see, oh, there were three different dyes. So there was like blue and some purple and maybe some green, something. So as the solvent moves up the paper, the dyes are carried with it and begin to separate. They separate because the substances have different solubilities in the solvent, right? So depending on how soluble that particular dye or whatever substance it is that you're testing is in the solvent that you've chosen, it will travel a different distance. The less soluble it is, the less it will travel. The more soluble it is, the further it will travel. So the substances have different solubilities in the solvent and are absorbed to different degrees by the chromatography paper. As a result, they are separated gradually as the solvent moves up the paper. The chromatogram, this thing, in figure 14.23, shows how the ink contains three dyes PQR. The name PQR because you don't know like the chemical name, or you don't want to you just want to be just label them, right? You're not going purple and blue and stuff. Sure.
Yeah.
Chromatography is used extensively in medical research and forensic science laboratories to separate a variety of mixtures. Okay, have they given any further detail about chromatography? Yes. Right, so here what we have, right, several dyes, different dyes were spotted on the chromatography paper and set up for chromatography. The chromatogram produced is shown below. So A, B, C, and D. Which of the dyes are pure substances and which are mixtures? So you can obviously see, right, B only has green, C only has yellow, so they're pure, whereas A is a mixture of red and blue, and D is a mixture of red, blue, and yellow, right? So B and C are pure, A and D are mixtures. All right, there's a bit of going further with starch hydrolysis and paper chromatography, so we're not doing that. We are doing the RF value, however. So, well, I mean, apart from separating the dyes and getting to know, okay, fine, so the different dyes. If you want to be more specific, or like it's not just dyes, okay, right? It's used in medicine and forensics, so you can use it for other purposes. And the starch hydrolysis thing as well, which right is going further. And so to be able to properly identify what substance is this, you make a calculation and get the RF value. So RF value, numerical measurements known as RF values, can be obtained from chromatograms. RF stands for retardation factor, right, which is basically a sort of reference to how far the solute, so the dye or whatever it was, moved up the chromatography paper as compared to how far the solvent went. So there you have, like, an RF value is defined as the ratio of the distance traveled by the solute to the distance traveled by the solvent from the pencil line. So starting from the pencil line, right? So starting from here, pencil line, and for example, the solvent went all the way up. So you take the measurement from the pencil line to the edge of the paper, and then you take measurements from the pencil line to the center of these dots, right? I mean, it should be, if you're taking the top of the dot or the center of the dot, it should be uniform, right? And then you take RF values for that. So you do that calculation. So the substance to be separated do not have to be colored. Colorless substances can be made visible by spraying the chromatogram with a locating agent. Right, that agent will react with the colorless substance to form a colored product. So even if you got like three different, like, yellow spots on the paper, that works. Right, it's only yellow because you're coloring it to to locate it. In other situations, the position of the substances in the chromatogram may be located using ultraviolet light. So just so you know, if they ask you that in your paper, here's a work example. So the following values were obtained for the chromatogram produced for the amino acid glycine. Distance traveled by glycine is 2.5 centimeters. Distance traveled by the solvent is 10 centimeters. The RF value comes up to be 0.25. Again, RF value depends on which solvent you've used. Different solvents will give you different RF values. So to refer that, you need to check a table or any like values for that particular solvent. Okay, it's not like you're using one solvent and getting an RF value and then checking the table for a different solvent, because it's not going to work that way. Right, so RF values are cataloged in data books for a vast array of substances. So for unknown substances, they can be compared with values in a data book to identify the unknown substance given the solvent that you've used. And as you can see, you got a decimal, like, right, number less than 0. The RF value can be anywhere between 0 and 1. It won't be less than 0 because 0 basically means the dye did not travel at all, or like substance did not travel at all, and 1 means that it traveled as far as the solvent. Right, so it's between 0 and 1, so it's right most cases it will be like a decimal number, but right, nothing beyond that. Clear? Yes? No? Okay. Then you've got criteria for purity. So in chemistry, a pure substance is one which contains a single element or a single compound not mixed with anything else. The measure of whether a substance is pure is known as purity. This is different. This is different to the everyday meaning of purity. For example, in the food industry, if bottles or cartons which are labeled as pure apple juice are sold in shops, then the label means that the contents are apple juice with nothing else added. Right? However, the apple juice is not pure in the chemical sense because it's got sugar and protein and fat and like I'm just saying like, it's got stuff in it, but that mixture together is known apple juice. It's just that you haven't added like extra sugar to it, or maybe chemical preservatives or other stuff, or coloring. So in that sense, it's pure, that you haven't added any other chemical to it. But in itself, it's not pure because apple juice itself is a mixture of different substances, right? So it's not chemically pure. It is, common terms pure. So, right, it contains different substances mixed together. The substances added here may include a preservative as well as other substances which are harmless to the person buying it, which is debatable, but then that's beyond the syllabus. However, in the pharmaceutical industry, purity is essential because there could be significant dangers to health if any other substances are found in medicine. So, drugs, right? Pharmaceuticals, medicines, drugs is a general term which obviously includes other substances as well. But right, that's just saying medicinal drugs or pharmaceuticals are manufactured to a very high degree of purity. To ensure that the highest possible purity is obtained, the drugs are dissolved in a suitable solvent and subjected to fractional crystallization. Purity can have an important effect on chemical properties of a substance. Pure substances will form predictable products in chemical reactions. So we did in stoichiometry, we did percentage purity of sodium hydrogen carbonate, right? And so if you're using pure sodium hydrogen carbonate for a reaction, you know what you're going to get. And if you've got impurities and they react as well, you'll get some other stuff that you weren't expecting. And so, right, those are unknowns. You don't normally want that. So pure substances will form predictable products in chemical reactions. This reliability comes from the fact that there are no impurities present that could start other reactions. Reactions due to impurities may interfere with the reaction that is being studied by a chemist. So chemists often use substances which have a high degree of purity when conducting chemical research. Throughout the pharmaceutical, food, and chemical industries, it is essential that the substances used are pure. The purity of a substance can be assessed by its melting point. So if a solid is pure, it will have a sharp melting point, as we did right in earlier chapters. If an impurity is present, then the melting takes place over a range of temperatures, and that means that at least one impurity is present. If there are more impurities present, then it will be, all over the place. Its boiling point, so again, a pure liquid will have a steady boiling point. If the substance is impure, then the mixture will boil over a range of temperatures, and you will not get, right. So, for example, water boils at 100. If there's impurities meaning some stuff that you don't want, right? So if there's salt or anything else in the water, then it will have a higher boiling point. And so if you put water and it's boiling at 102 or 104 degrees, that means there's impurities. right? And it will be over a range of temperatures. So, right, the whole concept of the temperature staying constant when the physical state is changing, that you won't see that. Then you can assess purity by chromatography. If it is pure, then during chromatography, as we just covered, you'll only see one result. It will produce only one well-defined spot on the chromatogram. If impurities are present, there'll be several spots. Okay. So that covers separating mixtures. Then we have qualitative analysis, where you are identifying substances or what substances are made of depending on their qualities, right? Some of the characteristics. So the branch of chemistry that deals with the identification of elements or grouping of elements present in a sample is called qualitative chemical analysis, or qualitative analysis for short. It does not deal with quantity. So you're not like, how much do we have? No. What do we have? That is the question. Right? So what and not how much. The techniques employed in qualitative analysis vary in their complexity depending on the nature of the sample. Right? So sometimes it can be straightforward, sometimes it will require some working. So it is sometimes it's only necessary to confirm the presence of certain elements or groups for which specific chemical tests or spot tests applicable directly to the sample may be available. More often, the sample is a complex mixture and a systematic analysis must be made in order that all the component parts may be identified. Often, the first simple stages of qualitative analysis require no apparatus at all. Things like color and smell can be observed without any need for apparatus. The following summary collects together information from throughout the book, which would allow you to carry out qualitative analysis. The material which is of extreme importance as far as your revision is concerned is that given in the following table. So 14.2, 14. So 14.2 is talking about the characteristic flame colors of some metal ions. Right, so if you burn a metal, it will give characteristic flame. So you can identify which metal it is based on that. Then table 14.3 is the effect of adding sodium hydroxide to solutions containing various metal ions, and then you get a colored precipitate or not, and does it dissolve in access or not. Then you've got table 14.4, which is the effect of adding aqueous ammonia to solutions containing various metal ions, again whether it gives a precipitate or not, whether what's the color of the precipitate, and whether it dissolves when you add excess aqueous ammonia. Right, we've done this in earlier chapters, but they've, as they said, they've summarized it and brought it back all over here, and this is stuff that you need to know, especially for P4, right? But it can be in P1 and P2 as well. Or in case of IGCSE, that would be paper 2, paper 4, and paper, I don't know whether ATPs like paper 5 or paper 6, but yeah, like for the extended syllabus, not for the core. Okay. Table 14.5 is a variety of tests for aqueous ions, and 14.6 is test for gases. So let's go through these. Appearance of smell. So preliminary examination of substances will give you a start. The appearance or smell of a substance can often indicate what it might contain. Right? So observation is that it's a black powder. So it could be carbon, right? Or it contains oxide ions such as carbon oxide, right? So, sorry, not carbon, copper oxide, in this case, copper 2 oxide, or it also could be sulfur ions in copper sulfate, right? If
Yeah.
if the substance is pale green, it has pale green crystals, then it could be a salt of iron 2. If it's dark green crystals, it could be nickel 2. If it's blue or blue green, it could be some salts of copper 2, right? Other than uh, copper sulfide or copper oxide, right? Because we did that, the black powder. If it's yellow brown, then it contains iron 3 salts. And if it's like the term used is pungent. If you want to get a taste of that, you can smell bleach if you have bleach at home, right? So that's the smell of ammonia. And if it smells that way, then it probably has ammonium ion, so it's an ammonium salt. Then we come to flame colors. And if a wooden splint which has been soaked in an aqueous metal ion solution, so they actually use an acid and other stuff, right? They're using wooden splint over here. There's another apparatus that is used. Platinum wire, I believe, is used, if I'm not mistaken. But yeah, this also works, obviously. And so you add the solvent, and then you dip the wooden splint into that solution that you made of the metal ion, and then you put it in a flame, right? And it is held in a colorless Bunsen flame. So, right, the flame itself does it's blue, basically, like the regular flame, right? So it's not itself yellow or red or green or something. Obviously, like flame itself, like flame is not colorless as such, right? So the regular flame is, they're calling it colorless. And so when the flame, as you can see in the picture, it's hitting the wooden splint which is soaked in the metal ion solution, and so the metal ions are burning, and then you're getting a colored flame above that, right? And so depending on the color that's being produced, you can detect you can come to a conclusion that, oh, these ions, these metals are present. And so the caption for the image says that the green color being produced is characteristic of copper. And so here's a table, right? Group 1 ions, right? So they have a charge of +1 only. And so if you've got lithium, it will be red, sodium will be yellow, potassium will be lilac. Group 2 ions, calcium will be orange red, barium will be light green, and copper, which is a transition metal, will have a blue green flame. So a flame color is obtained as a result of the electrons in the particular ions being excited when they absorb energy from the flame, which is then emitted as visible light, right? So some physics for you over there as well. We did come across this when we were talking about, I believe, nuclear physics, right? And so when electrons are excited and then they lose their energy, they emit electromagnetic radiation. It could be visible light. And also when you heat metals and they become red hot, and so that is you are like you're able to see that, so that they're emitting red light. When they become hotter, they emit infrared, and the temperature range was mentioned. The physics books, I don't recall it from memory. And white is hotter than red. So if something's white hot, that means it's like really, really super hot, right? And then white basically means that it's emitting the entire spectrum of visible light. So, right, these colors are because the electrons are being excited, and so they are emitting visible light. The different electronic configurations of the different ions therefore give rise to different colors. Then you've got aqueous cations, right? So stuff that for which possibly a flame test would not work out. So in this case, you're adding dilute sodium hydroxide. Aqueous sodium hydroxide can be used to identify salts of aluminum, calcium, chromium, copper, iron 2, iron 3, and zinc. Right, when present in aqueous solutions, all metal cations, and you need to know the oxidation like number of these guys, right? So if chromium, you should know it's like chromium is 3 and zinc is 2, and they're all metals, so it's plus, right? There's a part of positive charge, they're losing electrons. So all metal cations form insoluble hydroxides, right? Except for sodium and potassium, and ammonium is not a metal. So when sodium hydroxide, so obviously you can't use sodium hydroxide to test for sodium itself. The color of the precipitate and its behavior in excess sodium hydroxide solution will help you identify the metal. You can see over here, if you have a white precipitate, it's likely to be aluminum or zinc, right? The precipitate is soluble in excess, giving a colorless solution. If you have white precipitate that is insoluble in excess, then it is most likely calcium. If you have a green precipitate that is insoluble in excess, then it's chromium. Light blue, insoluble in excess, that's copper 2. Green precipitate, which is insoluble in excess, and if you leave it standing, it turns brown near the surface, that would be iron 2. And leaving it to stand and turning brown near the surface is going to help you distinguish it from chromium, which is only green and insoluble. And then you've got a red brown precipitate, which is insoluble in excess, and that gives you iron 3. In the case of ammonium salts containing the ammonium ion, ammonia gas is produced on warming. So if you heat that solution, it will produce ammonia gas. And so if you take a damp red litmus paper, it will turn blue, right? And so that means it contains ammonium ions. The ammonium cation does not form an insoluble hydroxide because all ammonium salts are soluble. However, it forms ammonia and water upon heating. And so you can do what I just mentioned to test for that. I believe they do mention it later on as well. Yeah, over here, ammonia turns damp red litmus paper blue. We'll get to that in a while. So effects of adding dilute ammonia solution. By the way, just checking, you guys are following along, right?
Yeah.
Yeah.
Ammonia gas dissolved in water is usually known as aqueous ammonia. The solution is only weakly alkaline, which results in a relatively low concentration of hydroxide ions. Aqueous ammonia can be used to identify salts of aluminum, calcium, chromium, copper, iron 2, iron 3, and zinc. So the same ions. Now, right, if it's the same, then why do this? Well, right, the response is different, as we'll see in the table. And so when you take a sample, you actually do the test with sodium hydroxide and ammonium hydroxide or aqueous ammonia, both separately, of course. So you take a sample from the sample, a portion from the sample, and you first do the sodium hydroxide test and see the result you get. And then you take another portion from the sample and then you do the aqueous ammonia test and see the result you get. And then based on the combined result, you come to a conclusion, oh, so this is the ion that you have. So that helps.
Yeah. Okay.
Right, so the color of the precipitate and solution form identifies the metal present. So if it's white and insoluble in excess, you have aluminum, right? Whereas over here, if it was white and soluble in excess, it was possibly aluminum. So if initially you had something like that and it was soluble in excess sodium hydroxide, but it is insoluble in excess ammonium, aqueous ammonia, you definitely have aluminum, right? In case of calcium, there is no precipitate or very slight white precipitate, and adding excess doesn't give you anything. So if with sodium hydroxide you were getting a white precipitate and it was insoluble in excess, but you're not getting anything with aqueous ammonia, that means you've got calcium. So this way, when you're comparing the two results, you can come to a definite conclusion. Right? Green precipitate insoluble in excess, that's chromium. It was the same for sodium as sodium hydroxide as well. Right? And then light blue precipitate, the precipitate is soluble in excess and it gives a dark blue solution, so that's copper 2. Whereas over here the behavior was different, right? It was light blue and it was insoluble in excess. So again, comparing the two results can tell you it's definitely copper 2. Iron 2, right, is going to give you a green precipitate. It is insoluble in excess and it turns brown near the surface when it's standing. So same result as with sodium hydroxide. And for iron 3, red brown precipitate, insoluble in excess. So definitely iron 3. And then remember, for sodium hydroxide, you were going like, okay, it's either aluminum or zinc, right? Because it's white, there's a white precipitate and it's insoluble in excess sodium hydroxide. Sorry, it's soluble in excess sodium hydroxide, giving a colorless solution. And so this is how you're able to distinguish between aluminum and zinc. So with aqueous ammonia, aluminum is insoluble in excess, whereas zinc is still soluble in excess. Right? So if it's still soluble in excess, you're okay, fine. We definitely have zinc. So this is how these tests can be used. And right, initially you added dropwise, right? You don't put in excess to begin with because then you can't be sure what you're getting. Right? You need the initial precipitate formed. And in case of calcium over here, right, you're not getting anything, and you're adding a dropwise for the sodium hydroxide as well, right? So it's not just for aqueous ammonia. For sodium hydroxide as well, you initially added dropwise, and then you add excess. Right, so these are results, tests and results that you need to know, you need to remember. Right, here's an image of, this is like, this thing is definitely iron 3. Right, you're getting a red brown precipitate, and this thing is definitely iron 2 because it's giving you green and it's turning brown at the surface.
Yeah, okay.
All right, so here's aqueous ammonia being added to a solution of copper 2. The solution forms a gelatinous light blue precipitate. Over here you can see the precipitate is forming, and if you add excess, the precipitate dissolves and gives you a dark blue solution. Right, so if you were go to the lab, right, doesn't usually happen in schools and O Level and IGCSE, although many schools are incorporating labs, right? Even though you're not doing the practical, but being able to see the stuff, happening in the lab really helps with your understanding. So we could find a video after this and see that happen in the video at least. And also there's titration left, so once we're done with this, I'll give you guys a 5-minute break, and then we'll quickly cover titration, so we're actually done with everything. Okay, how much do we have left? I believe that's the last part. Yeah. So quickly, tests for aqueous anion. So we did cations, now we're doing anions. Right? In this case,
Yeah.
we are right. The tests are different. So for carbonate, if you add a dilute acid to whatever you have, even if it's in liquid form, right, you're going to see effervescence produced for carbon dioxide. And to test for carbon dioxide gas, so we can look at this table over here, right, it's colorless and odorless, and right, it is, if you're going to use an indicator paper or litmus paper, it will turn blue litmus paper pink, right? And because it is weakly acidic, a more proper test is bubbling it through lime water, and it will turn lime water cloudy white, right, or milky. Then you have, if there's chlorine in the solution, you acidify it with dilute nitric acid and then add aqueous silver nitrate. So first you add dilute nitric acid, then you add silver nitrate, and that will produce a precipitate of silver chloride, right? A white precipitate is produced, which is silver chloride. If you've got the bromide ion, right? Again, dilute nitric acid, aqueous silver nitrate, and you're going to get a cream precipitate, and right, so that would be silver bromide. Iodide, same thing, you're getting a yellow precipitate, and that would be silver iodide. If you've got nitrate, we did this, right? Add aqueous sodium hydroxide, then aluminum foil, and warm it. We actually did the equation for this, if you recall, right? In an earlier chapter. And so if you add sodium hydroxide and then aluminum and then warm it carefully, ammonia gas will be produced. And I already told you, ammonia gas, it is colorless and it is very pungent, right? It's a very stinging sort of smell. It is unpleasant. It will turn moist litmus paper blue. So you need to see the color change, you need red litmus paper, obviously. So you need damp red litmus paper and it will turn blue. Then you've got sulfate, and right, you acidify it, then you add aqueous barium nitrate or barium chloride, and it will, again, we've also done this earlier. So again, as I said, right, this is a summary of everything, all the different tests that have been mentioned throughout the book. And so what you're going to get is a precipitate, a white precipitate, which is barium sulfate. And the sulfite, right? So sulfite is SO3, sulfate is SO4. So they're different. So if there's sulfite, you add a small volume of acidified aqueous potassium magnate 7, KMnO4. And the acidified aqueous potassium magnet changes color from purple to colorless, so it is reduced. The sulfite is oxidized to sulfate.
Okay.
Right? Because potassium magnet 7 is, oh sorry, this is 8. This is a misprint, right? This should be 7. So potassium magnet 7 is an oxidizing agent. So when you oxidize sulfide, you'll end up getting sulfate. But the fact that it is changing color means it is being reduced itself because it's an oxidizing agent. So that's what happens with oxidizing agents. And so, right, that means that there was sulfite which could have been further oxidized to sulfate.
Yeah. Okay.
Then finally, you got the test for gases. So you've done some of these, right? The hydrogen gas is colorless and odorless. It does not affect moist indicator paper. What you do is you take a burning splint near the test tube that you think is producing hydrogen gas, and you will hear a popping sound, right? If there's a popping sound, that means hydrogen is present. For oxygen, again, it's colorless, odorless. It's not going to affect moist litmus paper or moist indicator paper. And if the splint is glowing, it will start burning again. Here's an image of that happening, right? There's oxygen on this thing. You take a glowing splint and it will catch fire because, right, oxygen is required for stuff to burn. Carbon dioxide we covered, ammonia we covered, sulfur dioxide, right? It is colorless and a very choking smell. It's very unpleasant. It gets to your throat as well. It turns moist indicator paper red, which means it's acidic. So red is acidic. If it's turning red, it means it's acidic. If it's turning blue, it means it's alkaline. So ammonia, it turns the indicator paper blue, right? For the carbon dioxide, because it's weakly acidic, it's not going all the way red, it's just going pink, so slightly. Other tests, right, for sulfur dioxide, it turns acidified potassium dichromate, so not magnet, but dichromate 6 from orange to green, Potassium dichromate is also an oxidizing agent. It turns acidified potassium magnets 7 from purple to colorless, also an oxidizing agent, and so sulfur dioxide is oxidized further. Then you've got chlorine, right? It is a yellow-green gas, which has like a yellow-green liquid, sorry, and it has a choking smell. I'm sorry. Yeah, we are doing tests for gases. I mean, you could have chlorine
Yeah.
liquid, but in this case, we're doing chlorine gas. So yellow-green and very choking smell again, right? And so bleach has chlorine. Sorry, bleach has ammonia. I'm sorry, mixing this up. My bad. So you got moist indicator paper, and it bleaches the moist indicator paper. So it actually, the indicator paper will lose color, right? After it initially turns pale pink. So it will turn pale pink and then it will lose its color. And so it bleaches damp litmus paper. And finally, you've got water, colorless and odorless. It's not going to affect moist litmus paper or moist, indicator paper. And remember the hydrous and anhydrous thing we learned, right? It turns blue cobalt chloride paper pink because the cobalt chloride paper is anhydrous. So while it's anhydrous, it's blue hydrated. When there's water of hydration or water of crystallization, right, it turns pink. Or you could use anhydrous copper 2 sulfate, which is blue, and when you add water, sorry, it's white, and when you add water, it will turn blue. And
Okay.
yeah, that's the end of that. So congratulations. Now, if
Yeah.
you just give me a sec, let me see if I can pull up a short video for these tests. If not, I'll just share the links later, and I'll give you guys just a 5-minute break, and we'll come back for titration. So just give me a moment. All right, so I've got the flame test here. You guys can see this. See that? Let's open this up.
Yeah.
It's taking a bit of time. One thing you see over here that they've actually taken the salt itself, so you can do that as well, and they're putting the salt directly into the flame. The previous one was calcium chloride. This is copper. The focus is on the metal, so calcium gave you that red flame, right? And copper is giving you this greenish flame. All right, so I believe they've covered the ions that we are concerned with mostly. Right?
Yeah.
Yeah. I mean, obviously, they haven't given, in the text, they haven't given you all the flame tests. Okay, what else do we search for? Test for cations. 11 minutes. Don't we have anything shorter? So these are all rather long videos, so I'll share them. You can look it up yourself as well. But yeah, I'll share this with you. And so this is obviously going to have, you can see aluminum, calcium, zinc, lead, right? And so you can see that for yourself, and that will help you sort of remember and actually get to see what actually happens when you're doing this in the lab. Okay, so I'm not playing that right now. And right, so with that, right, that's the end of this. See you guys in 5 minutes for titration. And right, so let's be quick, right?
Hello.
Allah Hafiz.